Hello, folks. This is another video in a series that I call Killing a Fly with a Cannon. It deals with the modeling and simulation of the single degree of freedom system, which is vibrating in a one-dimensional situation, obviously. And I'm going to be modeling it with the Catia V5 program. The reason I refer to this thing as the killing of a fly with a cannon is that this type of problem, there you can find it in pretty much any elementary vibrations book, and it's amenable to hand calculations. Basically, you have to know a bunch of formulas, and you plug it in, and it comes out. But I want to make sure that we can do this thing with the CATIA program, which is really not intended for simulating problems of this type. The significant difference between this particular video and the previous ones that I had created were the fact that those involved the time varying force. Okay, that's why in Catia, when we modeled this thing, we called it a load excitation. This particular problem is the base excitation or restraint excitation, as Catia calls it. There is no force involved, but you have to give the description of the acceleration of the base, and from that you have to infer what the displacement and the velocity, etc., of the mass is. These are very common in earthquake engineering, and for example, a car going over a bumpy road. Okay, so they're both base excitation. In this particular case, suppose that you have a water tower, which is modeled as a single degree of freedom system, and the ground or the base is subject to an acceleration. That reminds you of earthquake, affecting a building, for example, a tall building. Now the data is given here, so we have the weight of the tower, the top of the tower, and we're assuming that the shaft or the base here is massless compared obviously to the weight on the top, and the stiffness of this support. Okay, and we are assuming that there is a damping. There is a damping of 0.1, zeta equal to 0.1, which is 10%. Now, the idea is that we want to calculate the displacement, velocity, and acceleration of that top of the mass, basically on the top, as a function of time. Notice that there is no force here. Okay, so there's motion of the base that is making this thing to vibrate, and over a 3-second interval with zero initial condition. This is a problem out of Tedesco's structural dynamics book. And we are told that the ground acceleration is this particular modulation curve. Notice that this is time, horizontal axis is time, vertical axis is dimensionless, multiplied by g, and g is 386 inch per second squared. So I'm going to be using pound, inch, and etc. So in that unit, g constant is 386 inch per second squared. Okay, so we're going to be using the spring rigid connection, and these are graphs that are generated or obtained from Tedesco's book. Let me go back here. Tedesco's book, the bottom one is the global or absolute acceleration of the mass. Okay, the one above it is the relative velocity of that mass on the top, and the very top is relative displacement. Now, in base excitation problem, the relative displacement and relative velocity are the important thing, and of course, when it comes to acceleration, really is the global acceleration you're looking for, or absolute acceleration, which is essentially the relative one if you generated it plus the base motion, acceleration of the base, which varies with time. Now, I will compare it with the Catia results, but we'll do that after we do the modeling. Okay, so first of all, let me start with the part file. So here's a part, and immediately I change my units. So tools, options, excuse me. So length is going to be inches. Mass is going to be slinch, which is that unit that I showed you. Essentially, it's 12 slugs. Yeah. Okay, so mass is a slinch right there. And let's, what else do we need? Stiffness. Let's go to the stiffness. Well, actually, let's take the force. Force is going to be pounds, although I don't use the force here. But let's see now. What else do we have here? We have stiffness, pound per inch. That's good. It's already there. I want to get the velocity, acceleration inch per second squared. Very good. And velocity is inch per second. And the displacement, I think the displacement is already in that length. Yeah, there is no such a thing as displacement. So let me just make sure this, oh, actually there is a displacement, but let me see now. These are all, there is no such a thing as the displacement itself. That's going to be length, okay? Good. All right, so we're good here. And let's follow our methodology in the single degree of freedom system. There are several videos on this, maybe eight or nine video tutorials on this SDOF, single degree of freedom system. I'm going to create 2 points. One is at the global origin right there. The other one is a few inches away, maybe 10, I don't know, 5 inches away. That means nothing. This dimension, 5 inches, means nothing. So I'm going to put a line between this point and that point. And yeah, let's put a material on this thing. Aluminum, dummy. We have to do these things, but the material properties, the mesh of this line that we're going to do, the beam element, the cross section, these are not going to come into the picture because we dramatically reduce, for example, the stiffness of the aluminum to 0.1. That's pretty much nothing, and the density of it is 0.1. This is about 20,000 times smaller than the density of the aluminum. But we need to do this. There's no way around it. Okay, that's pretty much it. So we're going to go to generative structural analysis. Let's see now. We don't really have to do static analysis. We don't need to do that. And we can go directly to frequency analysis. Now remember, if it was a load excitation, okay, then we do need a static case. Now there are several problems that I've done with where load is a function of time, which is applied to the mass, and there I had to do static analysis regardless, but not in base excitation or restraint excitation, as Catia calls it. So we go to frequency analysis. Okay, first thing we're going to do is to mesh this thing with beam elements right there. And we're going to use a minimal mesh, so all I need is one element through that. And the reason I have to do this is that the only way I can define my spring going from this point to that point, which represent the tower's base, is by doing these things anyway. And then we're going to do the, what is that, the 1D property. This is the support. Some dummy cross-section with the dummy value for the radius of it, so that's going to do it. Now, I'm going to hide this point and hide this point, okay? So this end is clamped, and this end, because it's a single degree of freedom system, can only move in one direction, y direction. So I'm going to do user-defined in the direction y, so it's fixed in all direction except that it's free to move in the y direction, right there. This is pretty much what I did with the other problems involving single degree of freedom system. Okay, good. Now we're going to create our connection, general analysis connection. This is going to be the first component. Second component is going to be this other end. Okay. And we need a mass here. We need a mass. So there is a lumped mass or distributed mass right there. And the value of it is this number. It's 85,000 divided by 386. Turn it into slingsh, and that's going to be this number that I have here, roughly 220 slinches. So we say, okay. Now, if I run this thing, I will get the frequency of the natural frequency of this structure, single degree of freedom system. So we can see that it's running. Now the problem is that it says, hey, this is a single degree of freedom system and you're asking for 10 frequencies. Okay, that's my mistake. We have seen this in several times. You go to this frequency case, instead of 10, we just ask for 1. Good. Now we're going to run it. Okay. So if you look at the frequencies, the list is going to be only one number, and it is this, and that is not correct. Now, notice that I have not even defined my spring here yet, so that's what we have to do. We already defined the connection there, and now we have to go to this user-defined distant connection property and select that connection, general analysis connection. Click on the wrench and put the right stiffness in it, which is 15,000 pound per inch in the y direction. Okay, and that is this number right there, this number. Okay, all right, so fine. Now we're going to run it. Okay, and then we're going to check the frequency. It's 1.314 hertz. Okay, that's correct. If you do square root of k over m, you're going to get that 1.4. Well, it's going to in radians per second, convert it to radians per second to hertz. Is going to get exactly that number. Now, here comes the rest of the problem. First of all, notice that I need this Excel spreadsheet. Because this is how the acceleration is going to vary, of course, multiplied by multiplied by 386. Okay. Now, I have already created this. I'm going to read this modulation because you have to read this thing as a time modulation because you're going to need it. So let me do that now instead of doing it later. So let me go back to Catia. First of all, we're going to insert a transient dynamic response. That's what we're doing. And we're not doing load excitation. This is the very first video that I'm doing for restraint excitation. Now, first, let's select our frequency case right there. This is the one that we just did. And for restraint excitation, not load excitation, restraint excitation, it's a new one, and we say, okay, good. Now, since we're going to need the time modulation of that acceleration plot, so why don't we do that now? Right here is the time modulation. See that? Time, T. You click on it, browse, and there we are. This is the base excitation. This is the Excel spreadsheet that I showed you. It's going to be read into Catia, and we can actually check it out. We can go and plot it. So here is the modulation that I imported. Right-click 2D display, and there we are. Notice that this has no unit. This is time, and starts at 0.2, roughly 0.25. It goes all the way to 0.3, and then drops down to 0 after 0.8 seconds. Okay, good, good. All right, now, on the damping, double-click on the damping, click on the wrench. Not 1%, 10%. So that's going to be 10%. All right, close that. Restraint excitation, it says, okay, well, where's the modulation? The modulation right there. See that? Modulation. So we did it, which was here. Now this is for all three, right? But I really don't have to do anything with X and Z. I mean, you can read it, but the important one is down here. And I noticed that there is no way to get rid of this, or at least I don't know how to do it. So let me cancel that. Let me try it again. Okay. What is that? Yeah. Restraint excitation. Go to the second line. Second line is modulate or excitation in the Y direction, TY. Okay. Select that modulation that I imported. Now, even if you do it with the top and the bottom, it's not going to it's not going to have any effect in it. Now, notice that the multiplier is 300 and the multiplier is 386 inch per second squared. 386 inch underscore S2. Right there. You can see that. Okay. Now, these numbers are totally useless because they're not going to come into the calculation in this problem. This is a single degree of freedom system in the Y direction. X and Z has nothing to do with it. Okay. And then we say, okay. All right. Now, that's pretty much it. Okay. So let's go ahead and generate our plots. Right click. Now remember, we don't have to run it because this is all based on linear dynamics. Linear dynamics means give me the damping, give me the natural frequencies. That's all. And we have already done that. The natural frequencies we already calculated, the damping we just set it, and pretty much nothing else. So you put the cursor there, right click, generate 2D display. And these are things that we have done over and over in the last, in this playlist many times. So and then finish. It says, okay, what is the place? Where is the place that you actually would like to plot something about? It's node number 1, right? So I minimize this. I want to select this node. Actually, this is not a node. It's the end of the, where the mass is sitting, right? So I'm going to hide this and hide that. Then it allows me to pick it, this thing. And we don't want X and Z. Add. We say, okay. So this is generated. A couple of things here, we plot it, and it looks like that. You might say, what the heck is this? Well, first of all, this is in meter. And I can convert this to, I can convert that to options. No, sorry, not options. Right-click options from MKS, go to options define. Okay, now it's in inches. But these are nowhere close to this kind of a plot. This is displacement, okay? Nowhere close to this. So the reason is that this is the absolute displacement. I don't want the absolute displacement. I want the relative displacement. So I'm going to close this. Essentially, this is a totally useless plot, okay? So here's what I'm going to do. I go to sensors. See that? Sensors. Right-click. Create a local sensor. Okay, you put the cursor there, right click, create local sensor. Let me show you again. Put the cursor there, right click, create local sensor. It says, well, what do you want? Okay, well, I want relative displacement. I want this. Why don't I actually plot the acceleration first? I want relative acceleration right there. I want this. Okay, relative acceleration. We say okay. Generate it here. But notice that there is an exclamation mark here because you have to say, double click on it, double click on this. It says where? Well, it's there, that vertex. I'll say okay. This still needs updating, so right click, update sensor, just give it a few seconds. Done. Now, right click, put the cursor there, right click, create 2D display. There we are. Okay. First of all, the unit is wrong, so let's go ahead and make this thing, put the cursor in the white area, right click, options, not the MKS, the units that are used. Notice that now it's inch per second squared. But this has no resemblance to this acceleration. However, the reason is that the number, if you double click on the transient dynamic response solution that you ask for, you're doing it over 10 seconds. First of all, I don't want to do it over 10 seconds. I want 3 seconds, number one. Then, the smaller this number is, the choppier that plot is going to look like. So let me make it 200. And then say OK. And then double click. Ooh, it looks a lot better. As a matter of fact, you can see that it looks pretty much like that, except that, you know, it's there's a little bit of choppiness here, no problem. So let me go ahead and increase the number of the steps. So what's here? Double click, make it 2000. Okay, and now double click on this. There we are. That's a little bit better. Now this is the which can be compared with this solution, which looks pretty much the same. Minus 100 to roughly 70, and then dies down minus to 7. Now, if you want to move this thing, you can't do it. You put the cursor on the screen, options, under the title tab. You select the what is that? Top center. Say OK, and then it moves there so you can read it better. Now, suppose you want to get the relative velocity. You put the cursor right again on the sensor, right click, local sensor, relative velocity. Check it out, relative acceleration, relative velocity vector, right there. You say OK. And then double click on it. It says where I want this point. You say fine. And then put the cursor there, right click, local or update, not local. Once it updates, then you can plot it. There we are. Double click. Oh, no, sorry, not double click. It's not what I meant. Put the cursor there, right click, generate 2D display, and there we are. This, again, the unit is not correct here. It says meter per second. I'm going to put the cursor there, right click under options, choose the defined options define. Now it's going to be in inch per second velocity, and this has to be compared with that. There's the velocity, and the numbers are pretty much the same, 0 to 10, etc. And in fact, what you see there is this kind of a plot. Where is that velocity? Is this the velocity? Yep. This is the velocity. Okay. Close that. If you want the displacement, put the cursor on the sensor, right click, local sensor. You can do these simultaneously, but I've done separately. So relative displacement vector, you say OK, double click, select that point. We say OK, update sensor. And once it's done, right-click, generate 2D display, and there we are. And this is supposed to be compared to the displacement, which I believe was, this was acceleration, and this was the displacement. This is that. Okay, so I mean, this is not much different from load excitation, except that the steps involved in order to display these things is completely different. So I hope that you found this video useful. I'm planning to do 2 more problems on base excitation. One of them, a car, for example, going over a bumpy road, so that it's a base excitation problem, and we're going to do that, and then maybe another one later on. Good luck.